Since an object moving in a circle is constantly accelerating, there must be some net force acting to cause that acceleration. We define that net force as centripetal force. Now we know that the net force acting on an object is equal to its mass times its acceleration. In the case of circular motion, we know that there must be some force being applied towards the center of the circle in order to keep it moving in that circle. Since we say that the acceleration of an object is the centripetal acceleration, we call the force causing that acceleration the centripetal force. All we really do is substitute in the centripetal acceleration for the regular acceleration in our linear motion. Something to keep in mind is that the centripetal force is not a new type of force. It is just a name we give to a specific force acting towards the center of a circle, no matter what is causing that force to occur. It could be a string attached to a swinging ball, or the gravity of the sun pulling in on the Earth. Now we define centripetal acceleration as the velocity squared divided by the radius of the circle. So we can of course substitute in that velocity squared over r for our acceleration. So say we want to estimate the force a person must exert on a string attached to a 0.150 kilogram ball to make the ball revolve in a horizontal circle of radius 0.6 meters if the ball makes 2 revolutions per second. Well, we know the mass, radius, and time. Since we know the radius and the time of revolution, we can figure the angular velocity using our first equation. Remember, time in these equations is the time it takes to make 1 complete revolution. So if 2 revolutions can be completed in 1 second, then our time is half a second per revolution. This gives us an angular velocity of 7.54 meters per second. From there, it's just a matter of plugging that velocity into our centripetal force equation that contains velocity, mass, and radius to find a force of 14 newtons. So calculate the centripetal force exerted on a 900 kilogram car that negotiates a 500 meter radius curve at 25 meters per second. Looking at our knowns, we can see that we have mass, velocity, and radius. Everything we need to use our centripetal force equation. Awesome. Let's just plug this in, and we end up with 1,125 newtons of force. Here's one that's a little tougher. If static friction is what is keeping a car from slipping off of the road, find the coefficient of static friction. So in this case, we are looking at the friction of the tires on the ground and how much is required to keep the car from sliding off the road. We know that the force of friction acting on an object is equal to the normal force exerted on the object multiplied by the coefficient of static friction between the two surfaces. If we look a bit more closely at the forces acting on the car, we can see that the normal force equals the weight of the car since there is no vertical motion. And we know that the weight of the car is found by multiplying the mass by the force of gravity. We also know that the friction is acting to keep the car from slipping and is the only horizontal force being applied to the car. Friction must then be acting in the same direction as the centripetal force since that is the direction of the acceleration. We can say that the friction force is the centripetal force in this case. So centripetal force is equal to the friction force, which is found using the coefficient of static friction times the weight. Since the centripetal force and the friction force are equal, we can set our derived expression for the friction force equal to the expression for the centripetal force. Mass is found on both sides, so we can ignore that and plug in our knowns to get a static coefficient of 0.13. So centripetal force is just the force that is required to keep an object moving in a circle. Since it acts towards the center of the circle, the acceleration that we use in our equation is going to be the centripetal acceleration.